Hi, welcome to my talk. So, I'm pre-recording this talk here in my home office, mainly because I have two small toddlers who scream and yell and make a fuss at completely random times. They're kind of in a tantrum mode, so it's hard to do all this stuff live. At the same time, it gives me a chance to enhance the lecture a little bit, put in some MATLAB code, and put some nice images in. So what we're going to be talking about today is a method of devising a model for time series data. So generally speaking, you have like a whole bunch of observations, which are called snapshots, and you would like to come up with a nice equation to represent them, or at least represent sort of the dominant features of them. The method that we're talking about today is dynamic mode decomposition, which is a nice intersection between sort of data science and and operator theory. Traditionally, the operators that are used are called Koopman operators, and these are composition operators, usually over something like a reproducible kernel Hilbert space, or at least a Hilbert function space. Sometimes it's used over L2, but L2 you can't really do sampling, so you run into issues there. But certainly well defined over a reproducible kernel Hilbert space. So the general idea is that you have a collection of snapshots of a dynamical system. So these are sort of like still frames that you've taken from some sort of moving system. So it could be snapshots from say fluid dynamics, or it could even be a collection of pictures taken like in Roger Rabbit with a patty cake. So yeah, it's but the idea is that you want to take these snapshots and you want to be able to devise some sort of model for them. The Koopman operator perspective basically says that if you have a continuous time dynamical system and you fix a time step, then what you can do is you can treat that fixed time step increments as a discrete time system, and then you get a discrete dynamical system that you can then put inside of a Koopman operator, composition operator. And then what you do then is you can observe your time series data through the guise of what are called observables, which are really functions inside of a Hilbert space. And so the idea is that if you have an observable looking at a particular snapshot and you hit the Koopman operator on it and evaluating at the same point, then the result is the observable evaluated at the next time spot. And so basically you can advance your time series by using the Koopman operator, but with an observable or a function sort of in the way. And so the goal, generally speaking, is to take a collection of observables and then be able to reconstruct the operator, the Koopman operator, from them. So basically, the idea is that you treat the Koopman operator, all these snapshots of the Koopman operator, as sort of sampling points for the operator itself, and you try to build the operator based on that. And this is more or less the DMD routine. The reproducible kernel Hilbert space perspective takes a look at the adjoint of the Koopman operator, and the adjoint of the Koopman operator hitting on the kernel functions themselves basically advances the center of the Koopman of the kernel functions, if it's one of the snapshots, to the next snapshot. And so then what you can do is you can view this the adjoint of the Koopman operator acting on these kernel functions as advancing from one kernel function to the next. And then the play there is to deconstruct all these actions and put it into a finite rank representation, and then you take the transpose of that, and then that sort of represents the Koopman operator itself rather than just the adjoint. So that's nice, and I more or less explained how the operator part works. How do we get the model? Well, there's a neat little trick that you can find if you take the eigenfunctions of the Koopman operator and you evaluate them at a snapshot, and then you hit the Koopman operator against them. Then basically what you're going to find is that this eigenfunction on the snapshots really just turn into lambda to the n, where lambda is the eigenvalue for this particular eigenfunction, times the eigenfunction evaluated at the initial point. Or it might be m minus 1 and x0. And I'll put it correct up here. And so then what you can do then is you find a basis for your Koopman operator. We'll assume that the Koopman operator is diagonalizable. And then you have a basis for your Hilbert space composed explicitly of these eigenfunctions. And so then if you want to express your the state, if it's one-dimensional, then you basically just take the identity function, say gid of x maps to x, and decompose it inside your reproduced kernel Hilbert space. This assumes that the identity function is actually in your Hilbert space. And then what you can do is then you take that expansion and you put in xm, and then you basically get xm is a sum of exponentials. But then, of course, we usually care about higher dimensional systems, not just one dimension. And so then what we do is we take what is called the full state observable, which is n-dimensional. And so basically you take a look at each one of these dimensions and you do this sort of same breakdown. And then that gives you this vector of coefficients corresponding to each eigenfunction. And this vector of coefficients is then called the Koopman mode, corresponding to that eigenvector. And so then what we have is we have this collection of eigenmodes, eigenvalues, and the eigenfunctions evaluated at the initial point. And we have a series of these, or a sum for the finite data sampling. And and then that's the model. Now, presumably, we should be able to get the strongest modes off of the finite rank representation, and so then in some way we go ahead and we just restrict to the most pertinent modes, although me and my co-authors are still trying to figure out the best way of doing that. But the Koopman perspective has a lot of limitations. One of the biggest ones is that the discretization of the system itself. So if you take a look at a polynomial dynamical system, say x dot is equal to 1 plus x squared, you immediately have a problem. We can say let's fix the time step of say pi over 2, and then we try to take we try to evaluate what this discretization would be. Now I think it ends up being like a xm plus 1 is equal to tangent of 1 plus arctan of xm, I think. And so what you're going to run into, or not 1, it shouldn't have been pi over 2 there, sorry. But what you run into is if you just pick xn being 0, xn plus 1 is undefined. And this is a problem because in a reproducible kernel Hilbert space, if you want to have a composition operator, even a densely defined composition operator, it has to be defined over the entire space as a function. So so then we have holes in our function that is discretized, and even if we change the step size from pi over 2 to 1 or just h more generally, there's always going to be a spot that has a hole. And so so then that tells you that you can't really discretize a sort of unbounded system. And if you really want to guarantee that you have a discretization, you need to stick to something like global Lipschitz continuity. And once you have that, yeah, certainly you have solutions existing everywhere. But unfortunately, that is a very limited class of systems. I mean, quadratic polynomials are out. We just showed that. So then what we would like to do is we'd like to eliminate this Koopman perspective, because there's other issues. For instance, composition operators are pretty bounded composition operators are pretty rare. If you look at the Bargmann-Fock space, it's only az plus b, and the compact ones are where a is magnitude less than 1. So then we really don't have any hope of this DMD procedure converging to anything, mainly because we have modally unbounded operators. So and so then what we'd like to do is we'd like to avoid this Koopman operator and maybe see if we can analyze the continuous time system directly. The best way to do it is through what is typically called the Koopman Generator, and it's called the Koopman Generator because it's the generator for the semigroup of Koopman operators where you allow the time steps to vary. And but what you end up having there, when you take that perspective, you still have to pass through the Koopman operator. If you look at all the analysis techniques out there, the Koopman generator is almost always defined in terms of a limiting relation of Koopman operators. And so then that means you have to pass through the Koopman operator, which means you limit yourself with the dynamics. First of all, the first thing we'd like to do is to escape from that. And so we're going to sort of obviate the use of the Koopman operator. And so we're going to take a look at the Koopman generator directly, which is really like something like an orbital derivative. I'll have it written up here. And so in order to access that directly and avoiding Koopman operators, we introduce something that's called an occupation kernel. Occupation kernels are basically an integral after composition with a trajectory, and it's the idea is borrowed from the idea of Koopman measures. Sorry, not Koopman measures, but occupation measures, which come from optimal control. So but the difference here is that we're taking these from just measure theory and we're actually casting them into our Hilbert space framework. And once we do that, we can actually use them for projections and approximation theory. So that's going. We have that going for us. And so then that allows us to do a direct analysis of the Liouville operator, rather the Koopman operator. We are trying to get rid of the language of Koopman operator, or Koopman generator. So we'll just call it Liouville operator from now on. But there's one outstanding problem with the Liouville operator, and it's the fact that the Liouville operator itself is unbounded. I mean, it's a differential operator, and so naturally it's going to be unbounded. And so we'd like to come up with some sort of compact, modification of that. And this is going to come through the idea of a scaled Liouville operator. And this idea is borrowed directly from weighted composition operators. And we have a paper that relates that in particular coming out in a couple months. But the idea is that basically instead of just taking a look at the Liouville operator, we actually compose the observable that we're throwing in there with a times x for some a that is magnitude less than 1. And then we hit it with the Liouville operator, and then that composition of two operators actually ends up being compact for a wide range of dynamics when you restrict yourself to, say, the exponential dot product kernel native space, which is the Bargman-Fock space. So so when you have that, it turns out that you can do this whole DMD procedure, and you not only get like a nice finite rank representation, but you actually get a nice approximation. And if you use, say, a dense collection of what we call occupation kernels, then you actually have a guarantee as far as the convergence in the norm topology for operators to the Koopman operator. And this is a significant step forward because the rest of the field really hasn't been able to do that. When you restrict yourself to a Koopman operator, the best you can really guarantee is that you're going to have it bounded, and that's unlikely. And so the convergence results that we have so far for the Koopman operator are actually just strong operator topology convergence, which would hold for any bounded operator. There's nothing special about the Koopman operator. And so this represents a significant step forward, and it really motivates the removal of the Koopman operator itself from this analysis. And so so what I'm going to show you is basically that we can get norm convergence using our DMD routine, and it's we're really excited about that. In any case, thank you for listening, and why don't we go ahead and go to the next step. Okay, so the crux of all of this DMD stuff that we're going to be doing today comes down to about 4 lines. I lack a chalkboard, but I have children, and so I have a whole bunch of sidewalk chalk laying around. So up here at the top, we have the Liouville operator. So the Liouville operator we need to know by AF, and it acts on a Hilbert space. Generally, it's an unbounded operator, and this is most obviously coming from the fact that it has a derivative. So the idea is that the Liouville operator acts on G as sort of an orbital derivative. So basically, you take the gradient of G with respect to X, and then you multiply it by F, where F is generally your continuous time dynamics. And so then if you want to get at this from a data standpoint, you need to have a trajectory coming from your system. So the trajectory that we're going to be talking about here is this guy, a gamma. And so here we're saying that gamma dot is equal to f of gamma. So it's it satisfies our continuous time dynamics. And the idea is that we're going to observe one of these like trajectories, and we're actually going to observe several of them, and we want to convert them into some sort of put them in a container inside of our Hilbert space that represents this whole trajectory as a bit of data. What we're going to do that is we take a look at what we're calling occupation kernels, and these are these gamma sub gamma. So I put big gamma and subscript to a little gamma, and these occupation kernels basically represent functionals in our reproducible kernel Hilbert space, where that functional is integration after composition with our trajectory. So the trajectory is defined over, say, 0 to t, and it maps to, say, Rn. And so then if our Hilbert space it consists of functions over Rn, then basically we can compose a gamma of t for any time point t into g, and then we can integrate over all of those. Now, since this is pretty straightforward to show that this is a bounded linear functional, when, say, you have a set of a Hilbert space consisting of continuous functions, or even usually continuously differentiable to account for the gradient up there. And in this case, it turns out to be a bounded functional, provided that, say, gamma is, our trajectory is, say, continuous, or bounded measurable, things like this. So then what we're going to do in this interaction between the Liouville operator and our occupation kernels, this really comes from looking at the same sort of things that they do in for occupation measures. And so for instance, the work of Lasserre talks about this a lot. But basically what we're going to do is we can see that the dual product between the Liouville operator acting on a function in its domain, inner product with one of these occupation kernels, and this is in some sort of Hilbert space, is basically going to result in a difference of two different kernel functions, one at either endpoint of the trajectory. And why does this end up working? Well, if this is a trajectory for the dynamical system, so then if you take a look all the way up here at the top, if I put in the trajectory here, gamma to t, and for x, then that is basically the chain rule happening up there. And so basically that AFG composed with gamma sub t is really just a time derivative of g composed with gamma. And so then by taking this inner product, we can come back over here, and this ends up being replaced by delta g and then f over there on the other side. That is basically just undoing the time derivative, and that gives you g at the different endpoints. Actually, I made a mistake here. This is embarrassing. This should have been g inner product with these kernels. So k at gamma at t minus k at gamma at 0. And that's basically what you get. So yeah. So then that's the idea. So basically what the whole idea is that AF, then you can take its adjoint and apply it to the occupation kernel. And what is the answer you get is you get actually these kernels. That's what I ended up trying to put here. But you only have so much room for all this sidewalk chalk, and I made a mistake. Anyways, yeah, let's go back in the office. It's hot outside.
Okay, so let's take a look. All right, so here we're going to be talking about reproducing kernel Hilbert space H, and so RKHS, and generally we're going to think of it as being over Rn. We're also going to assume that it is sort of continuously differentiable. It is composed of, say, continuously differentiable functions. This works, for instance, if I were to take kxy to be the exponential dot product kernel. That would give me a reproduced kernel Hilbert space with that sort of property. In fact, those would all be real entire functions. You can also talk about kxy being a sort of radial basis function. So you can have, say, the Gaussian x minus y squared. And both of these would lead to reproduced kernel Hilbert spaces consisting of continuously differentiable functions. And the reason why you need that is because we're ultimately going to be taking the gradient of g. And so, so then we talk about the Liouville operator corresponding to continuous time dynamics f. And we're defining it over, or just giving this general definition where the domain here we're just sort of leaving ambiguous. Generally speaking, we're hoping that it's going to be densely defined at the very least, if not entirely defined over the Hilbert space, but that only happens in a few special cases. And this Liouville operator acts on G, a function in our Hilbert space, sometimes we call G an observable, by taking the gradient of G and multiplying it by the dynamics. And so the dynamics are a vector-valued function, and the gradient is a row-valued function. So, that's what gives you this. And so then if we take a look at a trajectory, gamma, going from 0 to t to Rn, we're going to assume that any trajectory that we're talking about here satisfies the dynamics. So gamma dot is equal to f of gamma. What you can do then is you can make these occupation kernels, which we talked about just a moment ago. An occupation kernel, it really comes from Rief's representation theorem, where basically we're representing this functional. So basically, if G is, say, assumed to be continuous, then if this is a kernel space, then this is going to give you a bounded linear functional for any trajectory. And so then therefore the occupation kernel represents this represents the data that is this trajectory inside of the kernel space. And you can actually evaluate this as a function itself this way, and you can get this by just taking the inner product of the occupation kernel against a reproducing kernel. So one immediate thing that we need is that the occupation kernel itself is in the domain of the adjoint of the Liouville operator, and not only that, but the action of the adjoint of the Liouville operator can be represented as a difference of kernel functions where they're centered at the endpoints. And that's really easy to see, and that just follows from here. This is really just, we just recognize that gamma is a trajectory, so this is in fact the time derivative of gamma, and then that means that you can use a chain rule, and the fundamental theorem of calculus gives you this. Then this on the right hand side turns into the G inner product against the difference of two kernel functions. So then at the end of the day, if we're going to take the adjoint and move it over to here, then we have a G on this side and a G on this side, and so then this and this must coincide. So that's how you get that. Okay, not too bad. But now that we have that, what can we do with it? Well, occupation kernels are themselves functions inside of a Hilbert space, and so if we have a whole collection of these things, we can actually talk about projecting onto them. So what are we going to do? Well, we take a collection of observed trajectories, so we've been watching the system and taking snapshots and stringing them into trajectories, and then we take a look at the collection of corresponding occupation kernels, and so this gives us sort of a basis for the span of occupation kernels. And so we take a look at this projection onto the span of alpha, and now we want to compute the matrix representation. Now I could talk about the projection onto alpha of AF star, and then have another projection before AF star, and do all that stuff, but then you'd end up having to deal with the entire Hilbert space. So it's simpler to talk about just restricting ourselves to as a domain and range as being just alpha. And the reason why you want to do that is because then we can talk about the eigen decomposition here, and the coefficients that we get on these, the vectors that we get out of this end up being a collection of coefficients that go on to the occupation kernels themselves. So then we can get a truly simple representation of our eigenfunctions just as a span of occupation kernels. Okay, so now let's take a look. So what is this matrix that we're getting? So we know that the occupation kernel, just from the previous page, the occupation kernel itself, when it's hit against AF star, gives us a difference of kernels. Now we're going to basically take this, and that's what we get, this column here, is that this is what happens when we take, say, AF star and we're hitting gamma 1. And we want to project this back onto alpha. And so if we take a look at this column and we hit it against this, that gives us the coefficients on the occupation kernels that would be the projection of this guy onto the span of occupation kernels. And so we do that for this column here, and then we do that for every single subsequent AF star acting on gamma sub m, right? And so then you do that one at a time, and so then the result is this matrix that tells you that if you get a function, say g, which is written as, say, wi of gamma sub I, then it tells you that if you take these w's, you put them over here, it'll tell you what the result is of this operator with a new collection of vectors on the other side. So, so just some basic linear algebra, but that's basically what you're going to get. Now, each one of these elements, so this here on the left is our gram matrix, so call this G, and every one of these elements can be computed through a double integral using our kernel, and everything over here is basically just an integral of the difference of these kernels. And all of this comes from the definition of occupation kernels themselves. Okay, so now let's say we've made this matrix. We can go ahead and find an eigendecomposition of it. But we want really an eigendecomposition of the transpose. And so sort of heuristically, we're thinking of this as sort of corresponding to eigenfunctions of the adjoint of this projection, AF star conjugated by these projections. And we would like to believe that it is really just this, but then again, we don't know that the occupation kernels themselves are going to be in the domain of AF, so this is sort of heuristic when we're talking about the actual Liouville operator. If instead we're talking about the scaled Liouville operators, then this would actually truly hold for, say, polynomial dynamics in any A magnitude less than 1. I'll talk to you what adjustments we need to make to convert this algorithm to an algorithm for scaled Liouville operators. But let's assume that works. So then what we do is we take a collection of orthonormal eigenvectors of this matrix, the transpose of what we were just talking about, and these are going to be our eigenvalues. You can get back to an eigenfunction representation inside the Hilbert space itself by taking a row vector of your basis and hitting it against this column vector that was your eigenvector, and then you normalize by this. So your gram matrix will help you find the actual norm inside of the Hilbert space. So what you get then is you try to take the identity function, and so this is x is the identity function of x. It just gives you x, and this is also known as a full state observable. So we're going to go ahead and expand this. Now keep in mind this is vector valued, and all of our eigenfunctions are scalar valued, and so what we're going to do is we're going to look at each component of the full state observable and compute this this inner product separately. And when you do that, this gives you what we call the Liouville mode, or in the Koopman case, it would be the Koopman mode. Now, all you do is you just take each one of these guys and you can expand it in terms of your integrals, and in terms of the. What you need to do then is you take each one of these guys and you expand phi I in this way, and when you do that, this is what you get for your Koopman modes. It's actually really, really straightforward, and so basically it's just a collection of just straight integrals of your trajectories times these coefficients that you got from the eigenvectors, and then a normalization constant coming out of there. Okay, so then you get sort of, for every, you have an identity function and you have this expansion here in terms of phi I, and then what do? Well, you go back and you say, well, what good were these eigenfunctions anyway? Why did we want these? Well, if you take a look at the Liouville operator and acting on an eigenfunction, what you can do is you can notice that if you take a trajectory, x of t, that satisfies our dynamics, and you take a look at the composition of them and you take the time derivative, what that can be spun out to is you can see that through this chain of equalities, this eigenfunction, the derivative with respect to t, is equal to lambda times the eigenfunction itself when composed with the trajectory itself. And this, we know from just straight differential equations, can be written like this. It is just the eigenfunction evaluated at the initial point times some sort of exponential, where the exponential growth depends on the behavior of the exponential depends on the eigenvalue. And so then, at the end of the day, you just go ahead and you say, okay, now instead of just a general x, let's say I'm just taking a look at it, x of t. Well, x of t is just the identity function on x of t, or the full state observable on x of t, and I can expand it like this. So where instead of all of those phi I on x, I now have phi I on x of t, which I know is equal to this. And so there you go. You have a model. If you know your eigenfunctions, at least you know what they do at a certain point, and you know your eigenvalues and your Koopman modes, or Liouville modes in this case, then you can have a model for your entire system. And that allows you to make predictions based on the data you've seen. And this was all constructed straight from the data, and there really wasn't any crazy linear algebra floating around in here. Now, what changes when we talk about scaled Liouville operators? Well, back over here, we end up having, instead of this, we have a gamma 1 of t, and we have a gamma 1 of 0, and up and down. And over here, it would be a gamma m of t and a gamma m of 0, and that would change that matrix, and nothing else changes. You can continue going through here, and you do all the same calculations. The grand matrix doesn't change at all. And the only thing that comes out at the end of the day that you're going to be concerned with is whether or not you fit this equation here. And using a little bit of movie magic, I'll put a theorem that we have here where you have to make a few assumptions, but when it does work out, it works out fairly well. And so I'll show you some examples where we can play around with this a parameter, and I'll show you it doesn't seem to really change a whole lot as far as our features. So yeah. What's nice about the scaled Liouville operators is that we know we're working on some sort of compact workspace. We've observed these trajectories in some sort of finite area, and that's where all of our data comes from. And so then you can choose an a that is close enough to 1 so that you don't actually change any of the points inside of this compact workspace by any sort of measurable amount, or at least up to sort of like the rounding error of the computer, and still get a compact operator. And so then all the trajectories that you observe, they don't really change that much under the adjustment of a. And so then what you can do is you can just go ahead and use that as your, so you can use that a value for your Liouville operator and do all your analysis on that. And this is a compact operator, and it turns out that the DMD procedure will actually converge in norm to that operator. And so then you can go ahead and use these scaled Liouville operators instead of a standard Liouville operator when you're actually doing sort of a dynamic mode decomposition.
Hey, welcome to a segment that I call MATLAB at midnight. And this is because midnight is when my children are asleep and I actually can work on MATLAB. In any case, yeah, so what I'm going to show you here is just some basic DMD code that we put together. This is sort of a simplified version of what we're actually using, but hopefully it's enough to get the point across. And yeah, so let's go ahead and get started. Okay, so we will go ahead and start going through the code. Let's see. All right, so to start off, let's just walk through the surrounding code. And so this is where we load in the data. And the data that we're using here is the cylinder flow example from the Kutz's book, which I showed you just a little bit ago. Or maybe I think that's a little bit later in the next segment, but that's fine. You'll see the book. In any case, so this is a cylinder flow example. That little snippet I had in the very beginning of the talk is basically what that data is. And so, basically, so here I'm loading in the data, and I'm putting in all this big matrix called W, which is a sort of three-dimensional matrix. And then basically what I do is I define a whole bunch of parameters. So H is a time step that was given in the textbook, and the width here is really just for display purposes later when we're actually trying to plot the results. Mu, actually I think mu is defined separately here, so we can get rid of that. So this is a mu that we're actually using. It's 5,000, which seems pretty big, but what we're going to be using is the exponential dot product kernel, and so that actually grows really fast depending on the data. So we need to damp it down quite a bit. You notice I actually also divided the data back here. I probably should consolidate that into mu at some point, but it was just while we're experimenting with the code, and eventually I got it working, and if it works, don't fix it. And here, this is the most significant portion for the data loading, and that's where I'm subdividing. So all the time series data out of Kutz's book, or anybody else who does DMD, is all done in snapshots. So I need to turn these into trajectories so I can put them into occupation kernels. So the idea here is I'm subdividing it into 50. There's actually 150 snapshots that are going to be going into this, and so then that means that we have trajectories that are all length 3, so they're not very long trajectories. I could make them longer and see what happens, but there's really no point. Yeah, so then from here there's just some parameters that we're defining. This is the code that actually does the subdividing, and so we don't need to look at that too much. And then this is where we get into the dynamic mode decomposition. So here I have a scaling value, and let's set this to 1 just to begin with, just so we can see what the normal Liouville modes look like. And so here I have the occupation kernel DMD demo code, again simplified from what we actually use. We have our Liouville modes, which is what we're really going to be using. This is where all the coefficients for the eigenfunctions go, and this is where the eigenvalues end up. We're not going to really look at these today. We're just going to look at the Liouville modes. So we can jump into this function and see what it does. And so it takes in our data set, it takes in the step size, and we tell it which kernel, but in this case we're only using one kernel, so it's really not used. We set a mu parameter, and we set our scaling parameter. So if you read through here, you don't have to look too much. It has a description of what the matrix should look like for the data set. And so basically the first dimension is trajectory, the next one is the dimension, and the next one is the time. And H is the time step, as we said. And the kernels we're going to be using is this. So it's the exponential dot product kernel, but I also throw in a parameter mu to rescale the data, so to make things tractable. And A here is the scaling parameter for the scaled Liouville operators. So there's really one big trick that goes on in here. And the idea is that in order to make a gram matrix, we have to do sort of a, let's see, so we had 150 snapshots. We're dividing into trajectories of length 3, and we are taking that information and we make basically 50 trajectories. So this would be a 50 times 50 double for loop here, and MATLAB is famously bad with for loops. There's some sort of technical overhead that goes on in there. I've never really been sure what that is, but if you exceed 2 for loops, your code is hosed. There's nothing you can really do. So here, in order to make our gram matrix, I took advantage of the fact that while MATLAB is really, really bad at for loops, it's actually really, really good at vector multiplication. And so what I do then is I actually make smaller gram matrices. for each of the 2x2 matrices we need it, 2x2 two-dimensional integrals we need to make. And so, for instance, I have a row and a column where basically I take a look at all the pairwise combinations of these guys, and what you can do is you can actually just take the rows and the columns and just turn it into this term xy. And when you do that, you throw them into your exponential dot product kernel, and so there you go. That's a sort of gram matrix for this exponential dot product kernel. Now I am doing a Simpson's rule for integration, so I do a entry-wise multiplication here, and then I just sum and sum, and yeah, that's the integral. And it turns out MATLAB does that insanely fast. So and so then I do the same sort of thing. This is what I call the interaction matrix, and so this is basically where we're seeing the interaction of the Liouville operator hitting on the occupation kernel and then projecting, and then before we do the projection back. And so so basically this is a whole bunch of inner products of the difference of kernels with our gram matrix, with our occupation kernels. And so it basically the same sort of deal, except instead of using the entire trajectory for the row, I just use the endpoint. So I have the end and the beginning here. And then they all go in there, and yeah, we do again the Simpson's rule, but this time it is just a one-dimensional interval. Okay, cool. So so then that's what we do on the inside of this loop. We do it for each trajectory, and then we feed everything back into this gram matrix. So then after that, it's pretty simple. We take a look at our matrix. So we have I'm taking the pseudo inverse of the gram matrix, which really just does a SVD type of inverse, and I multiply it times what we call the interaction matrix, and I take its transpose, that's a little apostrophe there. Then I take the eigen decomposition and spit it into here. Now these eigenvectors correspond to this matrix, and we want them to correspond to eigenfunctions. And so, so what I do then is I normalize them for our Hilbert space, and that comes here using that gram matrix we just made. Okay, so then that's great. The eigenvalues I just put into a vector, and we're never going to use that, so no big deal. I keep saying features, but really that's Liouville modes. And so then I go ahead and I'm building my features here. And basically all that really does, and this is a whole bunch of stuff that goes in here, but what it does is you see that we're looping through here, and we're taking the last feature, adding it back to the other, but by adding each one over and over again of this. And so what we're doing basically is we're going through each one of these eigenvectors and taking a look at each one of their entries. We take that, we slap it against the integral of each one of the trajectories, and then we add those all together and we put it into a Liouville mode, or a feature as I called it here. And that's it. That's how you find the features. If you look at other literature doing DMD and stuff like that, it's a bit more complicated. So we're pretty proud that we got that narrowed down to being so simple. So then here we are, profit. We put everything into our outputs, and we're done. So after that, this is all just code to display the Liouville modes, and so we don't really need to go into that too much. But yeah, so here, remember, we're setting the scale value equal to 1, and now let's go ahead and run it. And this takes about 30 seconds or so. Okay, so here I have it showing a good amount of the Liouville modes, and so we'll just page through them, and basically you'll see what they look like. So these come in pairs of real and imaginary parts, and these are all just sort of similar to what you would see out of regular DMD. They are slightly different, but yeah, just want to give you guys an idea of what they look like. So these are the XI that go into building our model for our system. Okay, so now with that in mind, I'm just going to show you with A being something like 1/2, and you see that they actually don't change all that much. Okay, so here is what we get when we have A being 1/2. So the modes themselves, they change only slightly. But really, I mean, this is more or less the same set we just saw, which is interesting because that means that, given a different parameter, we actually get roughly the same modes. But the thing is, with A being 1/2, that's a compact operator. And so we're actually getting convergence to that one. And so, so that gives me some confidence to trust the results that we're getting out of these scaled Liouville operators. In addition to them just being compact, they actually seem to give more or less the same Liouville modes. So, in any case, with that, I think that's where I need to stop it. I only had about 10 minutes or so to really be able to fill in here. And yeah, so we'll go back to my office. So if you're interested in learning more about this stuff, several advertisements I would like to make. First of all, we have a workshop that's coming up on June 30th. This is part of the ACC 2020, the American Control Conference 2020. And yeah, it's going to cover like all these approaches using the Koopman operator and just occupation kernels and occupation measures and optimal control and control theory and etc. And so it's a full day workshop, and since the ACC is being run entirely online this year, for $120 you can go in, or $60 if you're a graduate student. You can go in and you can come listen. And I know a lot of people probably have leftover travel money because they don't need to travel. So I really encourage you to go and check it out. It's being run by me and my colleague Rushikesh Kamalapurkar. And so yeah. And other than that, I guess I should probably also point you to a few references. So I mean, we have a couple of papers up on Archive. One paper is up on just system identification and really introduces the idea of occupation kernels. And this one's submitted to SciCon, and it's been through at least one round of reviews, and I'm pretty confident it's going to get accepted this next round. And then we have another paper that we are doing a revise and resubmit on this DMD method, and that's posted up on Archive right now. I think that version right now is actually kind of an older version, and so we actually are beefing it up quite a bit for the revision. So keep an eye out for an update there. Other than that, my graduate student and I are also working on reformulation of these typical DMD, kernel-based DMD algorithm, and we hope to get that published as a technical note, and we'll have that up on Archive pretty soon. Just keep an eye up. Just keep an eye on my profile on Archive and also my website, which I'll update someday. But if you want to see more on the Koopman perspective, I'd really recommend you check out Nathan Kutz's book. This is a nice little book. It has some chapters on theory and stuff, but I mean, I'd really consider this sort of a gamut of different applications. He talks about video processing here. He talks about EEG, or ECOG in particular, not just EEG. ECOG really freaks me out. Anyway, but fluid dynamics, epidemic models, all sorts of cool stuff like that, and of course fluid dynamics. If I didn't say that already, I'm not sure. And so yeah, that's a cool book to check out on dynamic mode decomposition. Of course, there's also all of Mezik's work, which is really interesting. He has, I think, a really long paper called Applied Koopmanism that I'd really recommend you check out. Let's see, anything else I want to mention? Yeah, I should probably mention my sponsors. So most of this work has been sponsored by the Air Force and a few other directorates. So I'll put a thing up here. A lot of this is actually attached to my colleague Taylor T. Johnson, who is co-authored with me on the two papers I mentioned already. And Rushi and I have this one that just got awarded, a couple months ago. Other than that, I should thank my collaborators. So I have Rushikesh Kamalapurkar, who has been a close colleague of mine working on these DMD problems. Benjamin Russo as well. All the mathy stuff I take over to him. My wife, Forrest Rosenfeld, has been helping me pick apart time series data because I am a pure mathematician and she does neuroscience, and so we've been picking through a whole bunch of EEG type data, and it's been a tremendous amount of fun. And then also Taylor T. Johnson, who I mentioned before, who supported my work up at Vanderbilt when I was a research assistant professor there, or research professor there. And yeah, so I guess, and yeah, I guess I should also mention all my students. So I'll put their names here. These are my graduate students or undergrad students who are working with me on various aspects of dynamic mode decomposition, either from a pure mathematical perspective or from a data perspective. And yeah, we're just having a tremendous amount of fun with us. Yeah, anyway, so yeah, thank you for watching.